In this video, we'll look at implementing Runge Kutta in MATLAB. After studying this video, you should be able to implement the classical fourth-order Runge Kutta method in MATLAB for a system of ordinary differential equations and compare those results with lower-order methods. Recall the classical fourth-order Runge Kutta method is implemented as follows. This is a one-step method, so it's y plus 1 is equal to yi plus phi times h. And remember, the Runge Kutta method is just saying that phi is some linear combination, a1 k1 plus a2 k2 plus, for a fourth order, we go to a3 k3 plus a4 k4. We have a linear combination of function evaluation, so each k is a function evaluation. And for the classical formulation, the a's are a1 would be 1/6, a2 would be 2/6 or 1/3, a3 is also 1/3, and a4 would be 1/6. And as we discussed in a previous video, we can think of this formulation as basically a weighted average of these four different slope estimates, k1, k2, k3, and k4, to estimate our increment function and use that to step to the next time step, ti plus 1. Let's look at some MATLAB code to implement Runge Kutta. So this is an excerpt from the M file ODERK4sys.m. We see a similar setup here. We're going to put the y values in columns in a matrix, as we have been for all of our M files for systems of ODEs. And then in our time stepping loop, we'll simply go through and calculate each of those function evaluations. So we have k1 is our ODE function dy dt evaluated at ti and yi. And then we'll use k1 to calculate y mid 2, which, going back to the previous slide, that's this term would be that y mid 2. And then we'll use that y mid 2 here to calculate k2. Similarly, we'll use k2 to calculate y mid 3. And again, y mid 3 in our MATLAB code would be this term. And then use y mid 3 to calculate k3. And lastly, we'll use k3 to calculate y end. And y end would be the y value that we're going to use for the last function evaluation, k4. So we'll use y end to calculate k4, and then lastly calculating our increment function phi as a weighted average of those 4k values, and then using phi in our general one-step method equation to calculate all of our y values for the I plus 1 time step. So I've supplied that M file for you, so you will want to make sure that you step through it and understand how it's working. And I've also supplied an example M file applying the fourth order Runge Kutta along with Hume's method and Euler's method to the same differential equation we looked at previously, the second derivative of y with respect to t plus 9y is equal to 0. And that has the analytical solution of y is equal to cosine of 3t. And here we can look at those results. For the solutions, we see that the Euler solution is unstable already at t equals 4 seconds. The magnitude of the Euler solution, the error in the Euler solution is greater than the solution itself, so we would say that's unstable. The Hewn method solution and Runge Kutta solutions are much closer. If you run the M file yourself and really zoom in here, you'll see the Runge Kutta solution is extremely accurate. Based off visual inspection, you'll see those green stars are right on top of that black line for the analytical solution. You should be able to see in this figure here that the Hewn method, we have small error, but noticeable error. Noticeable error in the Hewn method. And I've generated a second plot here just so you can see that there is error, obviously, in the fourth order Runge Kutta method. But that error in the Runge Kutta method is on the order of 10 to the minus 4. So very small error, but growing. Coming back to that concept of stability again, we'll see the error is growing, but we would not say it's growing in an unbounded fashion. And we would say this solution is stable as long as the time span of the integration is not too long. We can see we're getting close to, at 4 seconds, we're getting close to an error around 0.001. The magnitude of our solution should be around 1, so we're still at less than 1% error. But if we say we're doing this out for an hour, t equals 3,600 seconds, we would start to say that this is an unstable solution because the error is overwhelming the solution itself. So this is an example of where the stability of the solution depends on the time span of the integration. And I would encourage you to maybe play with that, change the time span in the example M file, and make sure you understand how this Runge Kutta method is implemented there.